This section is going to combine a couple of sections that we've already looked at, which should make it at least a little familiar looking. We're going to be evaluating definite integrals using u-substitution and backsubbing. So we're going to take something that might be given in terms of x, temporarily use a variable u, and then put x back in the end. That's not new. And then we're going to evaluate a definite integral, means we're going to use fundamental theorem where we plug in the upper limit and we plug in the lower limit once we've integrated it. That's not new either. It's just we've never done both of those things in the same problem before. Later on, we'll also talk about evaluating definite integrals using u-sub, where we're changing the limits of integration out of like the x terms, x values that might be given to us, converting those to u values. We'll talk about that down the road. But to get started, the first couple examples are actually the same problem twice. So the first time we'll look at the first objective, and the second time we'll solve it using the second objective. So they want us to make a u-substitution, keeping the limits as x values, and then changing the function back into an expression with x variables like we did in the previous section, and then applying FTC. So looking at this function, the quantity that's going to a power here is x cubed minus 1. So I'm going to let x squared minus 1. I'm going to let u equal x squared minus 1. du then will come as a consequence of that. X squared will become 2x negative 1 has a derivative of 0, and then we do need to chain on the differential of x at the end. So when we rewrite the integral, writing u to the third will take care of this quantity. However, we still have to take care of the x as well as the dx. We have not yet accounted for those. So I'm going to go back to this du equation. I need to knock out an x and a dx, so I'm going to solve this equation for the x dx, which means I just need to divide away the 2. So the x dx that I need to take care of in the initial equation can be replaced with du over 2. So I'll put a du here, and I'll put a 1/2 out front to synthesize the over 2. This expression we can integrate just using power rule for integrals. We go up to u to the 4th over 4. I'm not going to put a plus c on because it's a definite integral. But I am going to substitute the x's back in for our u. So really my fraction out front is 1/8. The quantity I have to worry about is not u to the 4th, but how about x squared minus 1 to the 4th? And I'm going to plug in square root 2, and I'm going to plug in 1 and subtract. So I'm going to have a 1/8 out front. Plugging in square root 2 gives me, squaring that gives me 2 minus 1 to the 4th would be 1 to the 4th. Plugging in 1 gives me 1 squared minus 1 is 0 to the 4th. So I literally just get 1/8 for a final answer here. So the u substitution that we did here and rewriting the integral in terms of u is not anything new. Going back and putting in x squared minus 1 for our u was nothing new. The new part was going, oh, I've still got to put on my limits of integration, plug them in, and evaluate the expression, which isn't really new either. We've just never done it in the same problem as u-subbing. So on the next example, we'll do the same problem, looking at it a little different way. So in this example, we have the same problem. This time they still want us to make a u-substitution. So just like before, we're still going to let u equal x squared minus 1. du is still going to be 2x dx. And we're still going to want to rewrite the integral. We'd have u to the 3rd again. And then keeping in mind that to get x dx, the stuff we still need to substitute for, there it is. I would just want to call that du over 2, so I'll still have a 1/2 out front, and I'll still have a du here. But before we integrate, what we're going to do, you notice before, when I wrote the expression in terms of u, I just left the limits of integration blank. Because originally the limits of integration were x values. Those are not compatible when you have u as your independent variable. So I just kind of left them blank to play it safe. I waited until we had the x expression back in before I put those x value limits of integration back in. In this situation, I'm going to leave the u cubed here. I'm going to put in limits of integration. I don't want x value limits of integration. That's what they mean by keeping the function as an expression with u variables. That's what we have here. And then changing the limits to u values before you do the FTC. So my old limits were x equals square root of 2 and x equals 1. My new limits are going to be u equals something and u equals something. And to convert from x values into u values, I'm simply going to use the equation that bridges x and u together. So I'm going to take this old square root of 2 x value, I'm going to plug it in for x here. I get square root of 2 squared, which is 2, minus 1 is 1. Same thing with this. My old x value was a 1, so I'm going to plug 1 in for x. I'm going to get 1 squared, which is 1, minus 1 is 0. And since these are bona fide u values, I can put 0 and 1 in because that's compatible with my du in my integral. And now I don't have to worry. I can just call this u to the 4th over 4, or 1/8 u to the 4th. I don't need to back sub. I don't need to write u in terms of x like I did on the last problem, because I've got u values that are compatible with it. I can literally just plug these in. If they're u values, I can plug them in for u here. So I get 1 to the 4th, which is 1, minus 0 to the 4th, which is 0, and once again, I get 1/8 for an answer, just looking at it, in a little different manner. In this example, obviously we got some trig going on. We're probably going to need u-sub. Remember, when you're doing u-sub, you want to let u equal one thing in the integral and then have du be the rest of the integral. And it's okay to have u going to a power. So like here, secant's getting squared, so I might consider letting u equal secant theta, but the derivative of secant is not tangent cubed, so that's probably a bad idea. However, if I play it the other way around, if I let u equal tangent theta, it doesn't have to be tangent cubed. As long as u is tangent, I can rewrite the integral as u cubed, and I will therefore have tangent cubed. I will knock out all this stuff. It also works out well because du, the derivative of tangent, is secant squared. So if I'm going to rewrite this integral, I'm going to call it u cubed, and that'll knock out this. And I don't even need to put anything outside. I don't need to mess around with the constant because my du is literally the rest of the integral. Secant squared d theta. Secant squared d theta. So I can just straight up call that du. Now, if you want, you could go and convert these limits of integration into u values and tack them on here. Or you can just do the integration as is and then back sub. Instead of a u, I can put in a tangent. I can just call this tangent to the 4th over 4. And then since I'm back in theta, I guess it's not x values, but theta values, I can put in the original pi over 4 and pi over 3. So tangent of pi over 3, I don't have a unit circle handy. Pi over 3 is like this deal here. So it's a short distance, which is a half, and then a long distance, which is a square root of 3 over 2. So tangent would be sine over cosine. It would be second thing over first thing, which would give me square root of 3. sum that to the 4th power over 4. And then when I plug in pi over 4, I know that tangent of pi over 4 is 1, because pi over 4 is right down the middle of the quadrant where you have an equal x and y value. So of course when you divide those, you'll get 1. So square root of 3 times square root of 3 is 3. Squaring that would give you 9. So 8/4 would be 2. This would work, of course, just as well if you had changed the limits of integration and left this as u to the 4th using different limits.